Welcome to the first lecture of the course on electromagnetic fields and waves. Electromagnetics is a branch of physics or electrical engineering in which electric and magnetic phenomena are studied. Today we will start with the introductory chapter, which will be about the general aspects of the electromagnetic theory, together with some history and motivation. Ancient people learned about the magnetism from lodestones, which are naturally magnetized pieces of iron ore. They are naturally created magnets which attract pieces of iron. The word magnet in Greek means stone from Magnesia. Magnesia currently is a city located in western Turkey with a modern name Manisa. The earliest known surviving descriptions of magnets and their properties are from Greece, India and China around 2500 years ago. However, the first record of magnetism was done by Thales of Miletus in about 600 BC. In 1600, Wilhelm Gilbert the magnet described the behavior of magnets, and in 1784, Pierre Laplace introduced the concept of electric potential. And more significantly, in 1785, it was Charles de Coulomb who announced the law of electrostatics. In 1821, Michael Faraday demonstrated the principle of the electric motor, and in 1873, James Maxwell formulated the well-known Maxwell's equations. In 1888, Heinrich Rudolf Hertz demonstrated the existence of radio waves. And later in 1916, Einstein's general theory of relativity was developed. In 1948, Feynman introduced his diagrams for quantum electrodynamics. And of course, the story of electromagnetic theory continues today. Electromagnetics explains and deals with waves propagating in space and through material media. It also deals with waves that are radiated and received by antennas, waves propagating in transmission lines such as coaxial cables. Some RF components, such as those used in the RF front end and in the tower's bugs, are typically designed and understood via electromagnetics. Communications employing fiber optics and optical components are also a subject area of electromagnetics. Another subject that we can list would be noise and interference between electronic components. We can continue with topics related to electromagnetics, but these several examples hopefully give you already the subject area of electromagnetics. Why is it important to study and understand electromagnetic theory? The answer to this question is simple. Because in our world we are immersed in electromagnetic fields. Starting with electronic devices that we use every day, such as mobile phones, computers, TVs, to natural sources of electromagnetic radiation such as the sun, we are indeed immersed in electromagnetic fields. Learning the electromagnetic theory will allow one to better understand the world we live in. In the picture of this slide, you see a general depiction of the electromagnetic spectrum. The electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. The electromagnetic spectrum extends from below the low frequencies used for modern radio communication to gamma radiation at the short wavelength or high frequency end, thus covering wavelengths from thousands of kilometers down to a fraction of the size of an atom. In this slide, you see another picture of the electromagnetic spectrum. Here, a special attention is given to the transparency of the Earth's atmosphere as a function of the wavelength of the electromagnetic radiation. You see that the atmosphere is most transparent at two ranges. The first one is for the visible light, between the wavelengths of 450 and 750 nanometers. And the second transparency window is located at the radio waves range. Furthermore, most parts of the electromagnetic spectrum are used in science for spectroscopic and other probing interactions, as ways to study and characterize matter. In addition, radiation from various parts of the spectrum has found many other uses for communication. Historically, electricity and magnetism were treated as independent phenomena. In the 19th century, unification of electricity and magnetism took place. And after 1900s, electricity, magnetism and optics became one unified theory. Among the scientists, there is an elaborate study towards one single theory of everything. It aims at unification of the four main forces in nature. They are listed in your slide, and you can see that they are classified as the strong force, the electromagnetic force, the weak force, and gravitational forces. So far, the scientists were able to unify the electromagnetic weak forces, and the work towards unification still continues. Our lecture series will focus on electromagnetics. The electromagnetic theory is based on Maxwell's equations. These are the most general form of the Maxwell's equations. They are always valid. These equations deal with two vector fields, E and B, each of which have three components. Therefore, 6 unknowns have to be determined. The components of vector fields are related also to two source terms, the charge ρ and the divergence current J. The first two equations relate to a specific spatial derivative, the divergence to the source term. The source term for the electric field is the charge. For the magnetic field, there is no source term, or there is no magnetic monopole. Therefore, the divergence of B is 0. Equations 3 and 4 relate to a spatial derivative to a time derivative. A specific change of E and B in space, expressed by the curve, is only possible if there is a change in time. In addition, equation 4 says that in the case of the magnetic field, a current can be generated by a source term, the current. These equations seem to be very simple, but in practice one has to take into account all charges and currents. In a centimeter cube of a solid, there are about 10 to the 21 charged particles and 10 to the 20 currents. It is impossible to take all these into account. Therefore, another version of Maxwell's equation is often used, and they will be a subject of our lectures in the following units. Our approach will be based on, first, defining the basic quantities of electromagnetics. As a second step, we will focus on the rules of operation, such as vector algebra, vector calculus, and partial differential equations. And as a third step, the fundamental postulates of electromagnetics will be presented. Let's introduce the concept of a field. A field is a spatial distribution of a quantity which may or may not be a function of time. The source of electric field, for example, could be an electron or a hole. The source for a magnetic field is, for example, a current. Fields and waves are essential for the explanation of the concept of action at a distance. Action at a distance. It means that the media is not necessary. It refers to a model which states the energy translation without the necessity for a medium for that. Examples would be the light that we see every day coming from the suns or stars. Or, for example, the gravitational field between us, the earth, the moon, etc. And finally, the electric and magnetic fields. The interaction between the magnet is an example. The contents of the course could be divided into 3 sections. The first would be the definition of the basic quantities of electromagnetics. The second part will be to focus on the rules of operation of vector algebra and vector calculus and partial differential equations. And finally, the fundamental postulates are to be presented. In the next lecture, our subject will be the vector algebra and vector calculus. See you in the next lecture.